Good. Welcome to the Development Conference 2023 from Lattice. Today we would like to share a multi-camera solution in the industrial environment, especially on robotics and the AMRs. I'm Karl Wachswender from Lattice, Principal System Architect. I have with me two partners and two customers, Citobits and DP Control. So the CEO from Citobits, Pablo, and DP Control, Mario, the CTO. But over to Pablo. Maybe you introduce yourself.
Thank you, Carl. I'm going to keep my introduction short. So my name is Pablo Leiva. I'm pretty passionate about FPGAs. And we started with Citobits, was founded in 2020, a few years ago. And our main goal is really to support the customer adopting new FPGA technologies. That's where we go with simple to use, easy to use solid modules. And with our deep understanding of the underlying technology, is what we really want to do FPGAs easy to integrate into your designs. That's where our tagline comes, this squeezing out embedded performance, because we focus into small, integrated, and low power solutions.
Over to Mario.
I'm Mario Villar, CTO and founder of DP Control Italy. Our company was born in 2002, so we are entering the 22nd year of activity. We have been involved into design and study and development of multi-core and multi-processing architectures since the inception of the company. I'm the chief scientist also of the TTM group, which is our mother company. And together with our colleagues, we are building up a one-stop shop in terms of systems design, especially when it comes to video technology. Our knowledge and know-how in terms of video processing has been implemented over time, especially and cooperating with the major principal actors in the field of machine vision.
Thank you, Mario. And last but not least, Karl Wachswender. There's the picture for myself. I'm a principal system architect in Lattice, specialized on the industrial side, working since more than 30 years in the FPGA business. Started in 2021 in Lattice, and my history, I was also principal system architect in Intel PSG or Altera. And I would like to jump to the agenda for today. So what we would like to discuss at the beginning or to show to you is the video pipeline in industrial applications. After this, a little bit a step into the CPU versus FPGA topic on the architecture. We have also the FPGA topic on the values, low power, flexibility, size, and other topics included in the slide deck. Then we would like to show to you a Citobit solution, what Pablo have shared with the modules. Then DP Control's latest and greatest Avant implementation. And then I would like to sum it up. So let's jump into the video pipeline and high level. If you talk with industrial customers about video, you have on the right hand side the different swim lanes. It starts from LiDAR over machine vision, robotics, also the surround view topic for vehicles or off-road vehicles. A little bit in the other section, we have also implementation there. And in the middle, you see the medical topic and the scope cameras. And if you have robotics topics, you have all this navigation and also AI topics. And this brings me to the workloads. You have on the left-hand side the workloads. Low power edge AI is, I think, the biggest application on FPGAs. What we are seeing, we have a lot of support topics there. Customers are asking about object detection, counting, human presence detection, face tracking, eye tracking, all this stuff. But that is only a part of this machine vision topic. On the vision side, you have also this ISP or the image signal processing. You have the stereo vision. You have sensor fusion topic and processing, and a lot of more. So on the one hand side, AI is very important, but also the whole signal processing and implementation of a camera and the stream to the CPU that you can make the AI is a main topic there. If we look to the pipeline, what we see in the market, we'll stop in the upper left corner. A lot of designs use FPGAs in the sensor bridging side. So sensors on the one hand side, on the left hand side, get connected with our FPGA and get more or less the data streamed into a CPU. Why it is so important to have FPGA there? So on the first hand side, you have a bridging function between different protocols. It could be also PCI Express, this could be Ethernet, it could be USB, a lot of different protocols. And the FPGA is a perfect fit to handle this. And on the other hand, we have every year new sensors, and the customer would like also to add these new sensors to the applications. And the FPGA gives more or less the freedom that you can connect all the different sensors. If you go one down, you see also this image improvement, image signal processing topic. I think DP Control can talk a lot of stories about this. Perfect for FPGA to improve the image. DeFi in, DeFi out, and you see the difference on the picture, what you can optimize with the right algorithms. On the upper right side, you have the sensor aggregation. This means robot vendors would like to have multiple cameras, up to 12 cameras on, for example, Boston Dynamics robot, what you can buy. And they get more or less synchronized in the FPGA and then transported to the mobile processor or to the CPU or the NVIDIA processor in the back. You see also there is a perfect play from the FPGA side, from robotic arms down to AMRs. And last but not least, is maybe not very often in the industrial world, but we see this more and more in smart homes or in automotive side. Maybe it is splitting, that you're duplicating the streams out, that you have different screens, what you should handle, and also maybe different resolutions that you make upscaling, downscaling, rotating, and stuff like this. Again, a perfect solution for a perfect application for our FPGAs. This said, I would like to dive a little bit deeper, and you see this also in the workloads on the AI side. It's not only the bridging topic, it's the second workload we see is industrial AI topics. I have not really a robotic arm or the AMR on this slide. I was thinking to use other pictures there. On the left-hand side is an inspection camera in the top. I will bring up my laser pointer, then I can guide you through. So there is the cameras in the top. You stream the data into the FPGAs. This is FPGA board, and this is bridging work what we are doing there, and then we stream it into the NVIDIA card. You see perfect application for FPGAs. We have the connectivity under control. We have the deterministic delay, what we need there, and we have also possibilities for fuzzer and security. And the CPU, the NVIDIA or other CPUs, are handling the control system and inside AI, maybe ISPs running on the CPU side or runs on the bridging device. In the middle, workload consolidation, what we see more and more, it goes also in the direction to connect multiple camera streams on the left-hand side, bring this up for application like virtual workloads on the AI or the PLC topics or HMI topics where you have AI function up and running. And that's is more or less running then on the CPU in the back, like virtual control system, like multi-control functions, AI functions, and the FPGA plays again the bridging device, connectivity, deterministic delay, so you know which delay you have in the system, and also the security, the fuzzers topic is there. And last but not least is analytics. So if you build a digital twin, for a AMR or a robotic arm, you should have a lot of compute power in the system. You should collect more or less the data, and you have their example from the Volkswagen Industrial Cloud. They're collecting the data, building up a digital twin out of the factory, out of the robots, and can optimize the processes. And with this, you have multi-control parts in, you have multi-machine topics in, and again, connectivity bridging device on the FPGA to get the data from the sensors in to analyze the data. Same again on the deterministic side and the diffuser. So you see everywhere is connectivity important, bridging, real-time compute, and with this we are achieving a better implementation for our customers on the AI side. If we jump to the difference on the different implementation, I have their ASIC. It could be also a CPU, it could be a GPU. But we see the data is coming in from a sensor, and the first step what the CPU is doing, it's optimizing the picture with DSP functions, with sensor, with calibration, with something like this. And the software runs and makes all this manipulation of the bit stream. So this means we need in this moment their CPU power, and the CPU power is more or less blocked by the sensor to get the information. Then you select maybe a CPU to have a hardware acceleration unit on AI. You have then in the middle the AI engine, and that is in hardware, and you can stream the data through. And the CPU is only handling then the input and output. And then in the output side, to make this post-processing is again a software to make a optimization for your communication, whatever you would like to do. This means your CPU needs a lot of horsepower for your data stream. This means the ISP in the front and the post-processing consumes CPU power. With this, you get less CPU power for your application, what you would like to run on a robotic, on an AMR. You should have the bandwidth of the CPU power free for this. And this could be a bottleneck on power consumption, maybe on the calculation, what you can make, on the optimization, what you can make. In the FPGA, if you put this in front of a CPU, you see everything is in hardware. You have IP up and running in real time for ISPs. You have the acceleration hardware available, the data gets streamed in, and then you make the post-processing and it goes then to a CPU. This means we make a hardware offloading from this housekeeping or for this function, what you need in this pipeline. And with this, you can use your CPU in the back by 100% the performance what you get. We can make a deterministic implementation that the latency from the sensor input to the sensor output is always the same delay. And with this, you are very aligned with the needs on the industrial side from robotics and AMRs. That's more or less the different implementations, and what we see in the industrial world, more and more customers would like to have a bridging device plus hardware acceleration in the FPGA and use this in industrial environment like robots, like AMRs. I step back. What is a solution stack on our side? Solution stack is a 5-layer system. It means on the lowest layer you have the hardware platforms, the FPGA, eval boards, demo boards with different interfaces. Second layer is this IP, what you need in the FPGA to get the connectivity, get this ISP up and running. You have the implementation tool on the software side. And above, you have reference design. For example, sensor bridging or display network infrastructure or image processing. And in the top, you have the different application, and our customer design service team can help you on this. So this means with the 5 layers, you can easily build up implementation from, for example, MIPI to a MIPI. You can implement some display boards. You can implement some ISPs. So we try to help you on this side that you have a easier start, and you can start with a reference design with the Ambition stack. This said, there are multiple ways to connect then this bridging device from the sensor to the end device. So the last mile connection to the processor. It could be on the one hand side MIPI and PCI Express. You know, there are limitations on the distance, centimeter range. The cables are very expensive if you run it there. But some customers would like to do this in this way because they have a very compact system. We are offering also EtherCAT communication, 1 gig, 2.55, 10 gig, whatever you need. It depends a little bit on the FPGA or on the performance side, but up to 5 gig is the smallest FPGA possible to handle this, to connect the vision processing, what you have on the left-hand side, to the processor. You know, longer range, cabling is easier, and with this you can make your pre-processing or processing on the CPU about 150 meters away. And last but not least, we have seen also the needs on the USB side. USB is definitely also a little bit a limitation on the as distance, as mid-range distance, what we say there. But it's plug and play, and everybody can understand the USB connectivity. So what we have in a special FPGA, we have a complete endpoint, a USB endpoint 3.2 on the die that we can play USB 3 vision, and this can connect direct to the CPU. So you see, not only the input sensor side is important, there's also the output side, and in the middle you make more or less the implementation. So this said, I mentioned a lot of different devices. That is our portfolio. So you see on the left hand side a platform, and the platform name is Avant or Nexus. The Nexus platform was released 2019, and there was the Crosslinks device, the first device, and you see we have now 7 members of the NX devices. There are 2 more, but the Crosslink device is perfect for embedded vision. So they have the MIPI, DeFi in, hardened or not hardened, and the Certus or Certus Pro offers you a different connectivity and supports also MIPI. And with this, we have a very good portfolio for the customer to scale from hard MIPI interfaces over to 10 gig inputs, 5 gig. And if you need flash devices, you have the Mach-NX or the Mach-5. Mach-X05 NX devices. They are flash based and handles more or less the same traffic as the Certus or Certus Pro. This said, we have announced a new platform, and it's the upper line, Avant. Avant was released by last year. We have released them in last December. You will see also new releases end of this December with new features on the Avant. Avant E is available, and you see we are focusing more on the process data side to get faster throughput. So these devices have a higher performance, and also make more AI functions or add more AI function with IPs into the edge compute device from Avant. So this device is bigger, is faster, have the same values as the Nexus platform, low power, small footprint, and also easy to use, but gives us more headrooms in different applications. And this guides me to the next slide, and this is more or less the mapping of the FPGAs, that you get a little bit of feeling what you can handle on the workloads. I haven't shared this before, this IS40 device. This is our lowest FPGA, ultra low power devices, below 50 milliwatts. Can run object detection. This is a small device. This runs AI functions or some eye tracking and stuff like this. So that is handled by the smallest FPGA from our side. In the Crosslink designs, you see then a lot of ISP function, bridging functions, and those are functions there where you see multi-object tracking from the AI side. And with this, we get higher performance into the edge computing devices with the right processing, with the right interfaces for this, devices behind the camera. Then we have the Certus Pro. You see workloads are going up and up and up. stream cameras, multi-camera solution. You will see this in the C2Bits implementation. These devices are handling 10 gigabit interfaces and can handle really data streams from multiple cameras. And last but not least, the Ferrari out of our offering and the performance, and you will see on the DP control side, multiple camera solutions get streamed in, and this device handles all the different workloads. So that's an overview from the throughput side and from the performance side, what we can handle, especially on the AI workloads, what I have mapped in. So this said, edge computing is important for us, also AI and also image processing, there multi-camera solution, and that's our implementation, what you see on this slide for smart factories, from the robotic side, from human detection, from safety implementation, that people get not hit from robots or other topics that you have workloads in the smart factory. Everything runs on our devices, from single camera implementation up to multi-camera implementation, with or without multiple AI workloads. So the customer can build this together like a Lego system. This said, I would like to hand this over to C2Bits, that C2Bits gives a little bit of insight what they have done with our devices. And now over to you, Pablo.
Thank you very much, Carl. Then if you can go to the next slide, and then we can jump directly into the solutions that we are providing. So as Carl already mentioned, Lattice is providing different stacks. As the example that he put with the vision stack, we are on the first layer, would be on the hardware level. And what we try to offer is an easy solution to integrate Lattice FPGAs into the design. So we want to remove as much complexity as possible and as much sources of error as possible. So in this case, the solution that we are offering, and we have a family of products based on these concepts, is FPGA solder down modules. That means that you have everything that you need to interface, interact, and implement a design with Lattice FPGAs in extremely small and compact form factor. So most of our design, we try to go as small as possible, so we target the integration part and also the low power. The idea with these solder down modules is that you're going to reduce the PCB complexity. We try to isolate it as much as possible inside the module, so we can expose with bigger pads, with more spacing, with a higher pitch. So that at the end is going to drive down the cost of the PCB and the technology that you need to use. All the design has been pre-tested, so that's going to drastically reduce the chances of an error. Sometimes when you're doing your own design, you can do a wrong configuration, wrong connection that's going to force you to make a respin. In this case, all this part of the design is already solved, it's already pre-tested, so you can really rely on it that it's going to perform as you expect. And one of the points that I think is most important is that you can really focus only on the application. All the interfaces, all the infrastructure, that's already ready. You already spent the time for the verification to be sure that it's going to perform up to the maximum standards of the device. And then you can spend all your engineering time just doing really what your company is going to do best and put all the effort into your own IP. With FPGA-based modules, then we'll be building on top of what Carl already mentioned. Of course, one of the main advantages is deterministic and real-time reaction time, so you can offload all the complexity, all the software tasks that could run in a hardware-based platform from your software. So you speed a lot your CPU, the resources, you free them, so you can really run the application that you're targeting to run. At the end, what you are allowing is maybe an entry-level CPU or system on chip to really have high-end hardware capabilities, just externalizing that part of the process. At the end, also going with a solder down solution, we try to reduce the cost, to keep it to a minimum, to really be able to go into volume, removing all the connectors, so you can treat them as another part of your design, as another component. And we can go to the next slide. Going more in deep about the advantages specifically of our solution is that our family of modules, they have a unified architecture for the Nexus family. So we target multiple devices. In all of them, you can treat them the same way. So if you need to scale up your design, you need a bigger FPGA, or you have multiple projects, that will be not a problem. It's the infrastructure, all the tools, everything is going to be the same. Right now, we have solutions for the Crosslink NX, for MIPI and LVDS bridging. One of the examples Carl already mentioned, multiple MIPI aggregation, display bridging. If you need to do implementation of some high-speed functions, that's where the collaboration with partners like DP control is extremely valuable. We have also provided a built-in update mechanism, which means if you need to download new configuration for your FPGA, new bitstream, all that parts of the logic, you get already libraries, everything's pre-tested, so you can always upload and recover the image if something happens. At the end, we target the most common interfaces with the I2C and UART, and we have built in some extra features that at the beginning you don't see that you might need, but it's nice when you know that they are there and you can rely that you can use them. For example, we have some thermal management for the FPGA, we have the clock configuration. If you're starting a new design, you might not be sure if one clock is compatible or is precise enough exactly for your use case. Taking all that burden of characterization, and then the hardware solution that we offer, we can guarantee that it's going to work for your application with the performance that you need in the temperature range that you're targeting. We also have inside the modules some statistics of the usage and identification, unique identification per module. So you can also use that relying on your product, that you can trace that back to the lot and what was produced. And finally, but not one of the tracking these low power applications would be the support for multiple low power modes. So in some part of your design, the FPGA doesn't need to be on, you can turn it off. And there's only a small supervisor that keeps awake, just waiting for a signal to turn on that on again. So that allows you to not only is low power, but you can go really to extreme low power modes, saving some energy, especially important in battery power applications. If I go to the final one, we have been talking about the hardware, but at the end, you want to define a specific application. And that's what you can also provide some interfaces, some custom IPs that are already implemented and tested in our modules for most of the more common applications. Here we have, as an examples, multiple MIPI aggregation for virtual channels. It's one of the demos that we had running in events together with Lattice as an embedded world. We have also image stitching. We have also PCI Express solution, 10G Ethernet, and that's where coming back to the previous topic of this clock configuration. You know that the solution you're getting from the hardware, the clock is going to fulfill the requirements, going to be precise enough, so you're going to avoid any mistake that could force you to make a redesign of the board. The end could end up quite expensive and delaying your time to market. And at the end, just to finalize this part, all these interfaces I mentioned, they are pre-tested, so you can rely that they're going to perform to the maximum speeds that the devices support. And then if you need something on top, that's some custom development that could be also provided by us. From here, then I'm going to pass the word to the partner Mario from DP Control, where he can go a little bit more in detail with the solutions.
Thanks, Pablo. And yes, I will be exactly on the opposite side of the scale in terms of dimension, at least for the product we are going to show in these few slides. This has been a prime time for us and also for Lattice, if I'm not mistaken, in adopting a new architecture like Avant on a multi-sensor system. In practice, we set ourselves a challenge at the beginning of last year, and then we worked all along 2022 to get a job done, which was demonstrating how far you could go with Avant E in processing multiple sensors at the same time without using any frame buffer memory. Frame buffering, it's always a challenge when it comes to FPGA designs. It's always power consuming, it's complicated to manage. Thermally speaking, is always something problematic for the designers to take under control. And in most cases, is an added expense to your bill of materials when it comes to high performance video processing systems. But the higher the resolution you choose, the higher the frame rate you choose for your application, or your application simply requires, you cannot override the requirements in terms of getting your pipeline elastic as much as possible. So the memory is a key component in this design. There is a way out from this problem, and it's being faster. Having a 16 nanometer FPGA like Avant E allowed us to stretch the performance of our ISP cores to the maximum we have ever had on a live FPGA. And we were able to process 8 sensors, 4K, Sony image sensors, capture at the same time without using a single bank of dynamic memory in a single board. The board you can see in the picture on the right side of the slide, it's called the Tarantula. It's Tarantula because it's a funny name, just remembering the spider. It has 8 sensors attached. It's like the 8 legs of a spider. And in practice, this was the first attempt we made to raise up to such a high number of 4K sensors, all spreading out data at 30 frames per second towards a single Avant-E FPGA, 500,000 lookup tables. So inside this FPGA, there is a complete ISP per each channel. And so we are capable to transform the incoming raw data from the sensor, being dewired, being analyzed in terms of statistics, being processed in terms of color correction, defect correction, and the tone mapping down to the color correction, and then the streaming towards the output interfaces without going to a central memory. We have been able to squeeze the performance of our flagship ISP, which is named Ispido, up to 297 megahertz running on an FPGA. It's quite a prime time for us. ISP is not a simple task normally. It's a full streaming task. It's a computational intensive. The activity factor of the logic gates involved into the processing is normally in the league of 70 to 80%, where normal logic is instead on the opposite side of the scale, in the league of 10, 15, 20% at maximum. So we are getting the best out of this platform, and we demonstrated also and during the 2023 and in many public venues that this platform was perfectly working and also showing very low temperatures on the dies when running in live. Can we get to this next slide, please? This is some better insights on the board itself. The Avant-E FPGA is the bigger portion of the silicon you can see in the center. As I was already reporting, we connected 8 image sensors, 4K each, IMX334 sensors from Sony, and we are also able to process now the data at the rate of 2 pixels per clock, which allows high frame rate, high bandwidth, and even HDR processing of the data, which is the next milestone to be achieved on this board. This board is also peripheral rich because there is not only the need for having the incoming of the data, you should process and send somewhere. In this board, we were able to use many other high-speed interfaces like HDMI, a USB 3 connection, a MIPI connection towards a USB 3 transceiver. And also we were adopting a number of Raspberry Pi compatible interfaces that allow us to route the output of the ISP towards an external board, like for example, Raspberry Pi or NVIDIA Jetson or similar, where the FPGA is the key component to guarantee the lowest latencies possible, the highest quality of processing is possible, and delivering the highest quality to the end user.
Good. This said, so I think Mario and Pablo have shared 2 times the power consumption. I think the small modules from Citrobits offers you a very perfect implementation and a very low power implementation. And Mario shared this before with the 8 cameras. The FPGA was not really hot, so we had no cooling concept on the board. You can touch it if it runs. So there is really a low power implementation on the mid-range devices. From the form factor, different form factors you have seen, very small one for modules. You can have also a very big one, what you have seen on the Tarantula board. So it depends what you need, and we have their offering from left to right. If you need security on the devices, all the families have security support. Performance, perfect for the industrial environment, for the camera topics for ISP. I think Mario gave us there a really good insight. From the single event upset topic, we see a big benefit from the technology what we are using. There's 100 times lower SER. And lifetime, I think that's clear for the industrial environment. It's a minimum that we should offer 15 years, and it's supported by our devices. This said, I would like to share the last concept what we will have announced on the December 5th. It's a sensor to GPU topic. So again, in the middle, a bridge, what you see there with these green arrows. You have on the left-hand side the sensor, on the right-hand side the GPU. Now, I know the GPUs since years, but the GPUs are not really rich on interfaces, what you can connect A to B. So this means the customers have really challenges to connect this and stream in the right information or the sensor data in an easier way. So the bandwidth have sometimes a problem with the connectivity. We should have a scalable bandwidth topic on this side. We should have also a compute power on the right-hand side in the right way. And the customer is asking for low latency implementation from the sensor to the GPU. This said, we're working together with NVIDIA, and you see the logo on the right-hand side. I mentioned this, I think, 10 slides before, on the Jetson development kit. This Jetson device has two SFP Plus connectors. They're connected over 10 gig to our FPGA board. This FPGA board is the bridging device to get all this connectivity on the left-hand side done. So camera modules with MIPI streaming input. Also, the back channel with IAC is supported there. Or if you would like to have an FMC connector with SerDes channel, with LVDS channels, that is also connected to our FPGA. So this means you have on the left-hand side image sensors or some other sensors, RF sensors, A to D converters, what you can direct connect over the FPGA into the NVIDIA GPU. This complete design is an open source reference design, what you find on GitHubs, where you can stream in the sensor data. NVIDIA have a very rich software offering on the NVIDIA side and the Jetson side. You can control all the inputs and outputs over the software, and you get this Ethernet stream direct into the memory where you can make some AI calculations. So you see the facts there on the different connection over 10 gig, so you can run it also at 1 gig. If you would like, you have the FMC and camera connection, and the complete solution, what you have on the left-hand side, should be stay under 3 watts. So if you need more information, it's get announced on the December 5th. You find more on GitHubs, and we are also happy to share demos with you. This said, I would like to summarize this a little bit of what we have seen. So on the one hand side, for the compute, for the robotics, for industrial application, we have a complete solution stack for low power embedded vision and development. We have 2 strong partners like Citrobits and DP Control. They can give you platforms, complete implementation for sensor bridging, for sensor aggregation, or for image processing. So a complete solution from end to end. And the stack what I have shared for you, so the Envision stack what I have shared, it's really a multi-hardware platform. You can use it for Nexus devices, you can use it for Avant devices. We have an easy-to-use software implementation, a rich IP offering, and also Citrobits and DP Control is helping us on the IP side there. And reference design and customer design services is also very important stuff. This said, I think we are ready for your designs, and we can help with our partners, and we can help with our stacks to build a complete solutions. Yes, send us the question in on the Q&A side. We get more or less questions answered to you, and thank you for attending this session, and have a wonderful next session with the Development Conference 2023.